Welcome back. In part 1 we designed our layout for custom MacroPad. In part 2 we've designed the printed circuit board, and hopefully you have that ordered for fabrication from JLC PCB or similar. While we're waiting for that, we're going to work on the plates for the case. This keyboard will need a top plate, which is what the key switches snap into. See the PCB in the middle, and a bottom plate to keep it from scratching up the desk. We're also going to design some side walls to give it a nice finished look. And don't worry, I'm not expecting you to have any experience with CAD prior to this. We will start from the very basics. Rather than modeling anything from scratch, we want to use our hard work in KiCad as a starting point. So we'll go over to the PCB editor, go to File, Export, select Step File. Defaults are fine, and that's exporting that in our Macro 0 keyboard folder. Since I'm assuming no prior experience with CAD, I'm going to be using a free CAD software called Onshape, which you can find linked from the resource page. Go over to Onshape, sign up for a new account if you don't have one, and you can get started for free, and you can continue for free as long as you have a public account. The public account is really the only restriction. Anything that you design using Onshape, anybody else has access to. It doesn't really make a big difference to me. Obviously, if you're working for a company, probably want to get them to pay for Onshape. But the free account, I'm very happy with this as a hobbyist. Once you have your account set up, we're going to go to Create Document. I'll give it a name like YouTube MacroPad. Now, I think the first time you do this, it will ask about your preferences, and you'll have to set units and things like that. We'll be working in millimeters here. It opens us up in a tab. We look down here at the bottom called Part Studio 1. There's also an assembly tab over here. We don't want either of those. We want a new tab because we're going to bring in the step file that we have from KiCad. So click the plus sign, click on Import, and then we'll find our keyboard folder and find keyboard.step. We'll click that. Don't hit import yet though. If you import this as is, Onshape will helpfully add a tab for each diode on your board because they each have 3D models. We want to combine these to a single part studio. So make sure you click on that and then hit import. This can actually take a minute. It'll show you the progress over here. But once it's done, it'll add a tab down here at the bottom named keyboard, which is the name of our step file. And there it is. This should look a lot like the 3D view in KiCad, except it doesn't bring the silk screen over. That's all right. We're just interested in the shape. As you're looking at it, you can hold the right mouse button to rotate. You hit the F key to fit the view to everything on screen. You can also use this little cube here. You can click on the top to orient to that face. You can click to orient to another face, or if you click here, it'll flip around to the other side. So this will be the foundation for our top and bottom plate designs. Let's talk in detail about what we're going to build. And in fact, we're going to use Onshape to draw a side view of the parts we need in a little sketch. So let's come back over to Part Studio 1 for now. You right-click and rename this tab to StackUp, because that's exactly what we want to look at. Up here at the top, we want to create a new sketch, and we'll create it on the front plane, since this is a side view. And we can see the rectangle it draws here is sketch 1. We can hit N to bring us to a normal view to that sketch. Also going to hit the P key to hide the planes, because we don't really need those right now. We'll start with a rectangle to represent our PCB in the middle of the stack up. Up here in the drawing tools, we have lines, rectangles. We're going to draw a rectangle defined by 2 corners. One of them is going to be the origin, so we'll click on that. And we'll drag out to the right here to make something like that. Doesn't really matter because we're going to specify the dimensions numerically. Our PCB is about 100 millimeters wide. We don't care exactly for this sketch. and it is exactly 1.6 millimeters tall. I know that because that's the size PCB that we ordered from JLC PCB. You hit escape to unselect the rectangle. The normal cursor can be used to just click and drag these dimensions to wherever you want, or you can double click one to change it. We're also going to draw another rectangle. We'll use G for corner rectangle. We'll draw this to represent our top plate. Mouse wheel to zoom in, click the middle mouse button to move the view. If you accidentally rotate it, you can hit N again to get back to normal or straight on view. This will be the top plate, so it'll be somewhere above the PCB. If we hover over this line and drag up, we see a little dashed line that says we want to constrain it here. That'll work. And we'll drag over to somewhere around here and type in the dimensions. If the dimension you want isn't highlighted, move your mouse over to the other one, and you can type in whichever one you want first. This is going to be 100 millimeters wide, and the height is going to be exactly 3 millimeters. Why 3 millimeters? That's the thickness of the material that I'm using. So laser cut acrylic or plywood, that's a common thickness. 3D print this in PLA, I think that'll work pretty well. This is 3 millimeters for our top plate. Now we have a space between our top plate and our PCB. How do we know how much space to leave? Well, that's going to be determined by the key switches. Our key switches are going to snap into the top plate and plug into the PCB. So let's pull up the data sheet for our Gateron key switches. If we go back to the resource page, down here under reference information, we have a Gateron product data sheet. And these measurements are the same for pretty much any MX key switch. But as an example, we have the Gateron key switches up. And they show a couple of critical dimensions here. The main one we're interested in is the distance from under this flange right here to the bottom of the switch where it sits on the PCB. 5 millimeters. This part here sticks through the PCB. We've already seen the hole where that's going to go, and those are the pins. But 5 millimeters between the top of the top plate, we're talking about up here, and the top of the PCB. To tell Onshape that we want that dimension exactly, we'll use the dimension tool, which is here, or just hit D, and we'll click the top line here, and click the top line here, and then move our mouse somewhere convenient, click again to set the dimension, we'll type 5 millimeters. 5 millimeters is going to be the amount of space between this plate and this plate. So with our material dimension at 3, we don't have to actually calculate what the spacing is. Onshape will save us that headache. We click here, we can set another dimension. Drag over here, click. And instead of specifying it, we're just going to hit escape. So this is a informational dimension, right? 2 millimeter gap between here and here. So that's going to be the size of the spacers that we need to keep the top plate spacing correct from the PCB. We can actually draw a spacer in, hit G again for corner rectangle. We can click here on this top line and here on this bottom line. Spacers I found on Amazon are about 7 millimeters in width. That doesn't strictly matter. And our height is already specified, so that's fine. These two lines are blue, by the way, because they're not constrained. We haven't given it a dimension for where the spacer goes in this vicinity, right? We know it's attached to these two lines, we know its width, but we don't know where it's going to be, so we can still drag it around. For this particular sketch, it doesn't matter that it's unconstrained. We're literally just drawing on a napkin to see how things are going to line up here. All right, so let's put a key switch on our top board. We'll go to another corner rectangle, come back to our reference sheet, and we can see the whole key switch is about 11 millimeters from the bottom to the top. And then the keycap on top adds about 8 millimeters for an XDA switch. So we'll call that 19 millimeters. So back to here, we'll draw a rectangle from the top of our PCB up through the top plate. And we'll make it about 19. And look at the data sheet. It's about 15 millimeters wide. So we'll go 15 here, 19 here, and that'll represent our key switch sitting on the PCB through the top plate. Let's draw in our bottom plate. Yet another rectangle. We're going to make it vertical from the origin here. And draw out something like that. We'll give it 100 millimeters wide. And we'll type 3 again for the thickness. We can create a variable for that, by the way. I'll show you how to do that a little bit later. We'll just go ahead and specify that as 3. We need to figure out how much space we want to leave under the PCB. We have the controller mounted down there, and if you measure the header pins, it's about 9 millimeters from where they sit on the PCB to the end of the header pin. With the board mounted component side down, the header pins are the tallest thing there. We're going to draw a rectangle to represent that space. We'll start it connected here, and connected here. And we'll give it a height of 10 millimeters to clear that. So Onshape helpfully push this rectangle down to accommodate the constrained dimension here. And again, this one can slide around. We don't actually care. We're going to line it up with our spacer over here, because this actually represents a standoff. Right? These are the brass standoffs that we're going to use. You can see that there are a couple of different lengths available here, 9, 10, 11, 12, etc. These are all commonly available threaded brass standoff sizes. All right, holding our whole stack up together is going to be a couple of M2 screws. I like the M2 hardware because it's nice and small. I like these little laptop screws with a tiny little head, so you don't have to worry about them interfering with the key switches, even if you don't countersink anything. Instead of a rectangle for the screw, we're going to draw a line. L for line. We'll start it on the top line of this plate and drag down somewhere into our spacer. It looks like the screw could be anywhere from about 9 or 10 millimeters to, I don't know, 14 or so. So I'll drag one there, hit escape. I'll drag another one from the bottom plate up to here. And if we click D, we can drag out a dimension for these. So it looks like if the top screw is 12 millimeters, the bottom screw could be 6 millimeters. Those are both commonly available sizes. And that'll keep them from running into each other in the middle. We have all the hardware that we need to put this thing together. So you can go and order the 2 millimeter spacers, or if you're 3D printing your parts, you can design this appropriately. And the 10 millimeter brass spacers for the bottom, along with the M2 screws to put it all together. Last thing I want to do with this sketch is figure out how tall our walls are going to be. I like having the top plate a little bit wider, so it can have nice rounded edges, even if it's a laser cut sheet, and then have the walls come up to meet it. So we'll draw another corner rectangle, hit G for corner. We'll connect it to this corner of the bottom plate, and drag it up to connect it to the bottom of the top plate. We'll set the width here to be our material thickness, which is 3. And we don't want to set a dimension for the height. If we do, even if we just hit enter here, we're going to set off the red alert of over-constrained. Right? Everything turns red, all the constraints that are in conflict, and Onshape says sketch could not be solved. So that means you did something wrong. You can go in and delete constraints individually, but usually the easiest thing is to hit Control-Z. And in this case, that keeps our rectangle, but deletes the constraint that we were trying to set, which is fine. If we want to see how tall this wall is going to be, hit D, click on the line, click to place the dimension, but don't hit Enter, hit Escape. Again, that's going to make this grayed out informational dimension. If anything changes in our stack-up, like if we want 12 millimeter spacers here, our informational dimensions will change accordingly. I like 10 millimeters, that's enough room for the C-Picro. So that means our walls are going to be 16.6 millimeters to go from the bottom plate to just under the top plate. If you're tired of typing in the 3 for material thickness, by the way, there are other ways to set that. You can set up equal constraints to set all the dimensions equal, or you can use variables, which we'll talk about when we get to the plates. Hit the green check to say that we're done with the sketch. If you wanted to edit it again, you can double-click it here in the list. And if the view is messed up, you can always hit N to come back to normal, or click on the face on the cube here. We're done with this Part Studio, though. Let's create a new Part Studio. Right here, plus, create Part Studio. And we'll right-click to rename this one as Case. We'll use this to design the top plate, bottom plate, and the side walls. Remember that PCB we imported? Now it's time to actually make use of it. Up here in the toolbar, there's an item for derived part. I'll give you a minute to find it, or you can click here and search for it. We want a derived part to bring it in from another Part Studio. And click Select Part Studio, and we want the keyboard PCB that we had earlier. So we'll click on that, and it gives us a list of options. We don't want any of the diodes, we just want the keyboard PCB. We'll click on that, and then the green check mark to commit this operation. And our PCB suddenly exists in our 3D space here. The bottom of the PCB is currently sitting on the top plane. If you look at it right there, you can see that. We're going to be designing our bottom plate first, and we want it to be based on an offset plane. So we'll go to plane here to create a new one. We'll click on the top plane. That's the entity to base it on, and then set this to offset. We want it to be 10 millimeters lower, and then the material thickness is 3, so we'll go 13 millimeters lower. And if we look at our layout here, we see it actually went higher. So we'll click this arrow to flip it to the opposite direction. We go down below the circuit board. Perfect. Next to the green check, there's a little pencil icon. We can click on that and say bottom plane. And hit the green check mark. Now we can create a sketch on it. Clicking the sketch button here. We'll select our bottom plane in the features list. Clicking that here. And we'll give it a name of bottom. Hit N to come back to normal. We'll hit P to get rid of the planes because we don't actually need those. Middle click drag to bring our PCB over. And we can start designing our bottom plate. First thing we're going to do is draw a rectangle to represent the inside of the walls, basically the space that's enclosing the PCB. To do that, we'll do another corner rectangle and click approximately on the outside of the PCB, click again. We have no idea what these dimensions are, so just hit escape to skip out of that. And we'll use the dimension tool by hitting D. And we'll start with this top edge. Click the top edge, and click the top edge of the PCB. And we'll set that to 0.5, give us a little bit of wiggle room. Now, Onshape helpfully tried to scale the entire shape to give us that dimension, which is not quite what we were trying to do. Lines are blue, meaning you could drag them back out where they go, or we can set a negative dimension between these 2 points, meaning they should be the other way around. Negative 0.5, we'll move it out there. Same thing here. Click, negative 0.5, click, click, negative 0.5. And we have an outline rectangle around the PCB. We want another rectangle representing the outside wall of the bottom plate. But since it's identical to this one, we're going to make our lives a little easier by using the offset tool. I'll click that here in the toolbar, hit O, and then we'll click on these 4 line segments, say that these are the ones that we want to offset. You can hide the PCB now in the parts list over here, that way you don't accidentally click one of the lines on the PCB. and it defaulted to offsetting it inward. We want to flip it outward. And then the mouse cursor changed into this green check mark, so we'll click anywhere to commit that, and then give it an offset of 3 millimeters. We didn't offset the PCB border, by the way, because we wanted nice square corners, and our PCB has rounded corners on it. All right. If you're 3D printing your bottom plate and walls all in one piece, this is all the geometry you need to actually define that. Since I'm going to be laser cutting this, I actually need each of the walls to be its own part. We'll talk about that in a little bit. I'm going to hit L for the line tool, click on this corner, drag horizontal, double click to end the line, and repeat for a vertical line. Middle click drag to come over to the next corner, and we'll do the same thing. If you don't like click double click, you can also click drag to draw a single line. So click drag, release, click drag, release. Once we have all 4 of our corners boxed off like that, we have a couple more features that we want to see on this bottom plate, namely the screw holes. So over here in parts, we're going to turn our PCB back on. And in order to make use of geometry that exists on another sketch or another part, we're going to use a tool right here that says use, or you hit U, and that will let you grab something on another part or sketch and borrow it or project it into the sketch plane. So we want to click on the circumference of each of these mounting holes so that we have those in the bottom plate sketch as well. Make sure you click on the circumference and not the middle point. You can also use the middle point of a circle, but that's not what we're trying to do here. Hide the PCB again, and we see that we've successfully imported those 4 mounting holes into the sketch for our bottom plate. Now we're ready to start making parts. So we'll hit the green check mark to dismiss that. Next to the sketch button is the extrude button. We'll click on that. Click on the sketch in the list here. And it gets pretty close. It selected the walls to extrude. We also want to extrude the base though. And we wind up with a nice slab of bottom plate with mounting holes, 25 millimeters thick. It's a little thick for a keyboard base, a little thin for armor plating, but we'll go with 3 millimeters. I was going to teach you about variables though, so instead of typing 3 yet again, we're going to type £. It says new variable. Yep, we want a new variable. We'll do £thick. We'll hit enter. It says that's a new variable. What value do you want it to have? And it'll default to what you had there before. So 3 millimeters. We'll hit enter. We'll hit one more time to set that here. So £thick is now a variable. You can see it in our feature tree, set to 3 millimeters. If you wanted to go back later and change that, you certainly can. And you can use that anywhere in pretty much any parameter or dimension that you need to enter. Now if we rotate our part, it's starting to look more like a bottom plate. Last thing we want to do is hit P to show the planes again and make our PCB visible. We're going to double check that we went the right way when we extruded this. So we started from the bottom plane right there, and we extruded up toward the PCB. That's exactly right. We hit green check to dismiss that, and we can actually check it by selecting 2 parts in the 3D view. You can select this bottom face of the PCB and this top face of the bottom plate. And down here on the right, it'll say parallel distance between these 2 faces is 10 millimeters, exactly what we wanted it to be. That's looking pretty good. If we click on the top face of the cube here, we can even see everything lined up. Mounting holes line up and everything. Beautiful. That's starting to look like a bottom plate. We do need one more hole in the bottom plate though, and it's not for a screw. If you have a reset switch on the back side of your PCB, you might want to be able to push it without completely disassembling the keyboard. Or not, that's your call. If you do want a hole though, we'll double click on the bottom sketch here, and to bring it normal, hide the PCB to get it out of the way, and we want a new circle. So we'll hit C for cookie, also for circle, and we'll click, I don't know, somewhere around here, drag it out, click again, set the diameter, 2.2 millimeters, big enough for an M2 screw. It'll work fine for a reset hole. Hit enter, and we have a circle. Hit escape to go back to the cursor. The circle is blue, which reminds us that we did not tell Onshape where the circle is. Now, unfortunately, our PCB doesn't have any clues. There's nothing on here to indicate where the reset switch is, since it didn't have a 3D model. So we'll need to base the location of this hole off of something that we can find on the PCB. Like, how about this mounting hole? We go back to the PCB editor. There's a tool over here on the right, which is made for finding dimensions like this, the measure tool. We'll click on it. We'll come up here to the center of the top left mounting hole. And when we try to drag down to the reset switch, we see that it's still snapping to 45-degree angles, so we'll hit Shift Space to turn that off. And now we can click right in the middle of the reset button, and this will stick on the screen for us. It gave us a little pop-up here that gives us the as the crow flies distance, which is not super useful. Also gives us an X and Y distance, which is exactly what we need. So 49 millimeters X to the right of the mounting hole, and 7.4 millimeters down. We come back to our Onshape file. We can add a dimension with D from the center of the circle, with the center point, not the circumference. Drag over to the center point of our reset hole, click. We can set the as the crow flies dimension, or if we drag up a little or move up a little, we can set the horizontal dimension, or if we move right here, we can set the vertical dimension. So as long as we set two of those three, it'll exactly specify where this goes. I'll stick with horizontal and vertical. 49 millimeters horizontal. Click, click. I'll move this over here to set 7.4. Enter. And our reset hole is definitively located. Double check. 49, 7.4. Exactly where it should be. With the green check to exit the sketch. Hide the PCB. And we see that our extrude defaulted to not filling in that hole. If it made the wrong call for some reason, you can double click on the extrude here. And where it says faces, you can go in and toggle that face on or toggle that face off to include or not include it in the extrude. While we're here, we'll go and rename this as bottom plate. And in our parts list down here, we can also give part 2 a name by right-clicking and selecting rename. This is our bottom plate. Turn on the PCB to show the stack up again. F to bring it back to the visible area. And our stack up is looking pretty good. I think we're ready for a top plate. It's going to look very similar, only with more holes for the key switches. We'll start a new sketch from this button. Select the top plane in the feature list here. And we'll give this a name of top plate. N to bring it normal. We're going to hit P to hide the planes. And we're ready to start bringing in some geometry. The bottom plate is a little in the way here, so we can hide it from the parts list. And we'll create the outline for the top plate. I don't mind to have rounded corners, just like the PCB. So I'm going to use an offset. And instead of clicking each of the segments of this, we're going to right-click and say Select Tangent Connected Edges. And then ignore this for a second. It's mad about trying to flip this inward. But if we click this arrow to flip it outward, we're just fine. Click again to commit it, and we'll set the offset to 8 millimeters. Should give us a nice size top plate. We want to make sure that the square edges of the walls fit nicely under those rounded corners. We can turn the bottom plate back on to see that. That looks good to me. If that's not the shape of your dreams for some reason, you can always draw your own outline, dimension it off the PCB. And if you like rounded corners, you can use the Sketch Fillet tool here. Click on it, click to line segments, and you get a radius here that you can specify in millimeters. I'm happy with the rounded outline of the PCB. We're definitely going to need those mounting holes. So if you'll remember U for use, and we want to grab the circumference of the mounting hole, not the center. There we go. And the other type of hole that our top plate is going to need is for the key switches. If we go back to the Gateron datasheet for a minute, we can see right here that the dimensions of the key switch that are supposed to fit in the cutout is 14 millimeters this way and 14 millimeters this way. So we need a 14 by 14 rectangle. You're very familiar with the corner rectangle tool, so you might be inclined to grab that. But we want this particular rectangle to be centered on this big hole for the center post of the key switch. So instead of corner rectangle, we're going to grab a center point rectangle, which is the one that gets the R hotkey. And our center point is going to be the center of this giant hole, which is, you can see, is a anchor point. We'll click there, drag out, click, and set our two dimensions, 14 millimeters wide, 14 millimeters high. And there's the outline for our first key switch hole. For this MacroPad, you can do all 15 of them, probably faster than I can teach you a linear pattern. But just in case you're doing the 12 by 12 Mondo pad, we're going to do a linear pattern anyway. You'll find that up here in the toolbar. You click on it, and then we'll click the features that we want to duplicate, which is all four sides of this square. And by default, we have 3 copies of it going this way with a 25 millimeter spacing, and 1 copy of it going that way. We can click this arrow to flip this direction down, and we can double click this to set the number to 3, and we've got a 3 by 3 grid, which is not at all aligned with our key switches. Now you could use the dimension tool to check the spacing from this hole to this hole, but I happen to know it's exactly 19.05 millimeters. That magical number is also known as 1U. When you talk about a 1U keycap, that is the spacing. 2U is twice that. So we can double click on this dimension here. Instead of typing out that number, we'll give it $U and type in 19.05. Enter, enter, enter. And the horizontal spacing is looking pretty good. Double click on this dimension, #U, and there we go. All right, that linear pattern is looking pretty good. And those are the only ones in a regular spacing here. So we'll click the left mouse button to commit this linear pattern operation. We can do one more over here because these are all in a row. Our center point rectangle will be centered here, 14 by 14, with a linear pattern using all 4 sides. This time we only want 1 in this direction, and 3 in this direction, with the same 1U spacing as before. Oh, that looks like 4 in that direction. Finally, we'll do the last 2 oddballs here with a regular center point rectangle. Hit R to start the rectangle tool. Click the center point of the circle, drag out, click, 14, 14. And that's all 15 of our key switches. We'll confirm the sketch, start an extrude operation. And over here in the features list, we'll click on the top plate as the thing we want to extrude. That's a little thick by default. We can set this to pound thick. And we get a 3mm plate. Now you'll notice that it's extruded right through the PCB because they're both sitting on the top plane. We're going to give this a starting offset. We want to move this up, which is that direction, right? Nope. That direction. We're going to move it up. From this plane, we want it to be 1.6 plus the magical 5mm between here and there. 1.6 plus 5. There we go. We'll name that top plate. The green check to commit it. And just to be safe, we can measure between that face, and we should get 5mm. I don't think that's right. We should have 5mm from here to the top face of this. So let's double click on our extrude. We want our depth here to be 5mm to the top of this plate. So we'll subtract 3mm, bring it back down. There should be at exactly 2mm between these two faces. One there, and one there. Parallel distance, 2mm. That looks better. We can hit N to bring it back to normal view. We can turn on our bottom plate. And we have complete stack up here. You click again on blank space to deselect whatever's selected. One more thing to do in our parts list here, we'll click on part 3, hit Shift N to rename it, call it top plate. That is a functioning keyboard, but it's a little breezy, so we're going to put some walls on it to make it look like a finished product. To start with, we will go over to Extrude, and our bottom sketch is probably hidden, so we'll click on the visibility button here to show it. Click the top face of the cube to bring it normal, and we're going to hide these parts so they're not in our way. If you were 3D printing this case, you might want to attach the bottom plate to the walls and print them all in one piece. That would work fine. I'm going to be doing this as a laser cut, so I want these as separate parts that can have finger joints between them. So for that reason, I'm going to only extrude the 2 vertical walls, dragging a box around these 3 faces. And I'm going to make sure this is set to new rather than adding it to an existing part. The height we want for these walls, we figured out earlier, is 16.6mm. So we'll put that in. We'll call these vertical walls. The green check mark. And we'll extrude again. The top face to bring us normal again, and we'll drag a box around these 3 and these 3. Now, since we had other parts visible, it picked some of those up in the face list here. So you can see rather than just trying to extrude faces of the bottom sketch, it's also trying to extrude parts of the vertical walls. We can just click the X here to get rid of the parts that we do not want in here. There's our vertical walls. We could put the height in here again, or we can say up to face, and click on this face of the walls, which means they'll always match. These are our horizontal walls. We can check. Down here in our parts list, we can see that these parts are actually separate. If we'd chosen to add them to the bottom plate, they would all be one part called bottom plate. But now we have parts 4, 5, 6, and 7. Click 1, hit Shift N, call that wall 1, click again to unselect it, click the next one. We can see that these parts overlap because of the lovely flickering effect that we get here. That's exactly what we want for laser cutting. We'll be cutting out finger joints in those parts later on. We would be done if this was a Bluetooth keyboard, but since we have a USB port, we should probably make a place to plug it in. In order to cut out a notch on this part, we're going to click New Sketch, and rather than an existing plane, we're going to click this face of the wall. and it'll happily add a sketch to that face. Bring it normal like usual. And we'll hide some of these walls because they're in our way. Wall 1 specifically is the one we're trying to cut a hole in. And we need to figure out where to line up the USB port, because that's going to be sticking off the bottom of our PCB right here. We pop over to KiCad, we can use our measure tool, find a dimension from, let's go from the top edge of the board. We got about 11 there, about 21 there. Now we don't want to cut it too close because the plastic surrounding a USB connector is going to stick out the sides. So let's say we make that more like 9 and 24 looks good to me. We'll draw a corner rectangle using G to describe our notch. It'll be attached to this bottom edge of the PCB, so drag it out this way. Don't know what the dimensions are yet, so we'll just hit escape. We did measure our dimension from this edge to the edge of the PCB. So click there, give this a horizontal value of 9. And we have a dimension from here to the same point, which would be 21. We'll give it a height of 8 millimeters, so plenty of room to access the USB port. Remember, the whole C-Picro is about 9 millimeters tall, so that should give us plenty of room. All right, we'll rename this to notch so we can find it later. Green check, extrude, and we'll select our notch sketch. This time though, instead of adding a piece, we want the remove operation. And it's trying to merge it with the PCB, which is not going to work so well. The merge scope here that we want is with wall 1. We'll click on it, get rid of the PCB. And if we show wall 1, we can now see that we're putting a notch in it, sure enough. And this notch is aligned with the bottom edge of the PCB, right where our USB port is going to wind up. We'll give that the name notch. Green check. Looking a little square though. We'll use the fillet tool here to make it a little snazzier. Click on fillet, and then we're going to click on each of the line segments that makes up the inside edge of this part. Right, that segment, and that segment, that segment, and that segment. We can set a radius here. Let's say 3 millimeters, I think. Perfect. If you're 3D printing this, you can start exporting STL and printing parts. Don't forget you can add some more fillets just to make it fancier, and because you can show off to those poor chaps who have to laser cut flat parts. To export a part, you just right-click it here in the parts list, export, and for the format, you can either go STL, which is pretty common, or step. Some slicers take step files as well. You can even select multiple parts and export them all together as an STL. You can even export, if you're waiting for your PCB to come in, you can export your PCB and do a test fit with everything and see how it works. Someday we'll be 3D printing actual circuit boards, but not yet. For my laser people, we need some finger joints to fit these parts together. To add our finger joints, we're going to make use of a custom feature of Onshape. Find that in the icon right here at the far right of the toolbar, Add Custom Features. We'll click on Community Spotlight. And in the search field, we'll type laser joint. Enter, come down to feature script laser joint, and we can click on this feature script right here, and it says it is added to our toolbar. We'll click to close that, and now we have a drop-down here with a feature called laser joint. Click on that to add it to your feature list. If it has single selected here, we'll go to automatic. And we want to join parts from our list over here. We'll select the bottom plate. Wall 1, 2, 3, and 4. And by default, it's trying to put 3 pins in everything, which looks a little tight to me. So instead of setting this to 3, we're going to use adaptive pin sizing. With a minimum width of 3 millimeters, we get 1 pin in each of the walls. That looks good. And a maximum of 50 millimeters, we get a couple of pins in the bottom joints. You tweak that to your heart's content, and then hit the green check mark to commit it. For extra credit, you can add tenting feet to the back of the case. I'm not going to cover those here because the script is already over 15,000 words long. We're going to move right into exporting this for laser cutting. We'll make use of another custom feature here. We go to the Community Spotlight, we'll search for Auto Layout. And Feature Script Auto Layout, click it here. Close out of this. From the drop-down, we'll do Auto Layout. And it's going to look for all the parts with a certain thickness. Well, our material thickness is pound thick, so we can put that in here. And it's going to lay them out on a virtual sheet with certain dimensions. Doesn't really matter what those are right now, but you can see it's flattened all of our parts out to get ready to export them. With the green check mark here. This is a fairly destructive operation in the sense that it's completely rearranged our parts, but we can still go back at any time and edit a dimension or sketch or anything else. In our list of features over here, down at the bottom, there's something called the rollback bar. And if we want to go back to a point in time, let's say when we were extruding the walls, but before we put the notch in, we can drop the rollback bar right there. And we can see that our parts are all back together with no laser joints, no notch in the wall yet. We can edit any of these parts, and then when we're done editing, we can drag the rollback bar back to the bottom. The same process is actually what happens anytime you double-click on a feature to edit it. You're rolling back in time to that point in the process. Unless you click on this button here that shows Final, which will give you the end result after all the operations. Last thing we want to do before we get ready to export this is if we hit the F key, we'll see an odd little part over here. That's our PCB. It's not 3 millimeters thick, so Auto Layout didn't try to move it. But our CAM software is going to try to give us an outline for it unless we get rid of it. So we'll go up here to Delete Part. Now this might seem kind of destructive. We're going to click on the keyboard PCB to delete it with the green check mark, and it's gone. We didn't delete it completely though, because over here in our feature timeline, we still have the derived 1 part, and it doesn't actually get deleted until the very end here. So all of our references to mounting holes and outlines and everything else on the PCB are still perfectly fine. The only thing we really deleted is the part from our final layout. Easiest way I've found to export for laser cutting is a CAM application, which we can add from the plus sign here, applications called Kirimoto. If you don't have this installed, you can go to the App Store, type in Kiri, that's the one. You can install it, it'll ask for some authentications, everything's free. Now we can go to plus sign, applications, and add a Kirimoto tab to this document. In the Kirimoto tab, before we get too far, we're going to go up here to the mode dropdown and select laser. By default, it opens up the files import window over here. We just want to enable the button that says Part Studios. I'm going to bring in the entire case Part Studio. Click on that. We do want to group these parts, so we'll hit OK. And there's the top plate, bottom plate, and wall pieces. Not very well optimized for laser cutting. One very important setting over here is the kerf, basically how much material the laser beam is going to remove. If you have access to a laser cutter, hopefully you already know what this should be. If not, you may need to make a couple of test prints with finger joints. If they're too loose, it means your kerf setting is too low. If they're too tight, it means your kerf setting is too high. For SendCutSend, though, we want this to be 0 because they do their own kerf correction. We'll set that to 0, come over to the Export tab, and SendCutSend wants a DXF, so we'll download that. If you have your own laser cutter, you might want to export an SVG. I know that works well in Lightburn, or Kirimoto can even generate G-code for a laser cutter. Let's see how to order those parts from SendCutSend. Open that up from the resource page, and we'll click on Get Started. And browse files to select the DXF file we just downloaded. Give it a second to think about it. And sure enough, that's what we just exported. We've got mounting holes, reset hole, key switch holes, USB hole. Everything's in millimeters, that's right. We'll confirm. Select a material. I went with plastic, acrylic, black. Depending on which color you pick, the price is a little different. Definitely want 3mm material though. That is the thickness that we designed for in On-Shape. And this should come to about $20. The PCB is on order. Your cases and plates are on order or ready to print/cut. Once you have all the parts on hand, you're ready for part 4 of the series.